In the vast and mysterious realm of quantum mechanics, the fundamental nature of reality is not what we might expect based on our everyday experiences. Quantum physics reveals a universe far stranger than we could have ever imagined, a universe where particles behave in ways that challenge the very essence of logic. The dual nature of reality, central to quantum theory, lies in the peculiar behaviors of particles, often existing in multiple states at once, and only choosing a definitive state when they are observed or measured. It is a theory that defies classical physics, which governed our understanding of the world for centuries. At the heart of this revolution stands Erwin Schrödinger, whose thought experiments and theoretical work opened new doors to understanding the universe at its most fundamental level. The dual nature of reality emerges from the way quantum particles, such as electrons, photons, and atoms, can be both particles and waves, depending on how they are observed. This is known as wave-particle duality. In classical physics, a particle is seen as a tiny, discrete object possessing definite properties like position, momentum, and mass. A wave, on the other hand, is a continuous disturbance in a medium, such as light waves or sound waves, and is spread out over space. These two ideas, a particle and a wave, were historically thought to be entirely separate and incompatible. But quantum mechanics shows us that they are not only connected, but that particles can exhibit properties of both depending on the conditions. To understand this concept, it's essential to look at one of the most famous experiments that demonstrated the wave-particle duality, the double-slit experiment. In the 19th century, Thomas Young performed an experiment where light passed through two closely spaced slits and created an interference pattern on a screen behind them. This pattern, with alternating dark and light bands, was evidence that light behaved as a wave. However, in the 20th century, when the same experiment was performed with electrons, it was found that even though electrons are particles, they also created an interference pattern, just like light waves. The surprising part of the experiment came when electrons were sent one at a time through the slits. In this case, the interference pattern still emerged over time, suggesting that each individual electron was somehow interfering with itself, as though it were a wave, not a particle. This result was baffling and led scientists to the conclusion that the electron could not be fully described as a particle or a wave, but had properties of both. This wave-particle duality fundamentally challenges how we perceive the world. Our everyday experiences teach us that objects are either particles or waves, but quantum mechanics reveals that at a microscopic scale, these distinctions break down. The reality that quantum theory unveils is one where things do not have definite properties until they are observed. The act of measurement seems to force particles to adopt a specific state as opposed to existing in a superposition of possibilities. The electron, for instance, can be thought of as being in a cloud of probabilities, and only when we measure its position does it choose a specific place to exist. This phenomenon, known as quantum superposition, underscores how the very act of observation alters the state of reality itself. This revelation opens up a host of philosophical questions about the nature of existence and our role as observers. If a particle's behavior is defined only upon observation, what does that say about the reality we perceive? Are we, as conscious beings, creating the world around us simply by observing it? These questions are not just theoretical. They touch on deeper aspects of our understanding of consciousness, perception, and existence itself. In Schrödinger's terms, the universe may not be a set of fixed, predetermined events, but a vast collection of possibilities that unfold as we interact with them. Erwin Schrödinger, the Austrian physicist, who is credited with formulating the famous wave equation, became one of the most influential figures in quantum mechanics. Schrödinger's work built upon the earlier ideas of Albert Einstein, Niels Bohr, and Werner Heisenberg, who all contributed to the foundation of quantum theory. However, Schrödinger's most famous contribution came in the form of his wave equation, which provided a mathematical description of how quantum states evolve over time. His equation described the wave-like behavior of particles and allowed physicists to predict the probabilities of a particle's position, energy, and momentum. This was a groundbreaking moment in science, as it provided a more accurate way of predicting the behavior of particles than classical physics ever could. Schrödinger's work with wave mechanics revealed a profound connection between quantum mechanics and the broader fabric of reality. According to quantum theory, particles are not solid, defined objects, but rather exist as probabilities, waves of possibility that span a range of potential locations, energies, and momenta. When a measurement is taken, the wave collapses into a single state, which is the reality we observe. The wave-particle duality lies at the heart of this quantum phenomenon, demonstrating that our understanding of reality must be flexible and adaptive, able to accommodate the idea that particles can act both as localized objects and as extended waves of possibility. The nature of reality, then, becomes far more fluid and uncertain than we may have thought. Quantum mechanics forces us to reconsider how we understand the universe. In classical mechanics, objects are predictable. They have definite positions and velocities that we can calculate with precision. Quantum mechanics, on the other hand, challenges this determinism. Instead of a world governed by fixed laws that dictate the behavior of all things, quantum mechanics presents us with a probabilistic world where outcomes are not set in stone but emerge as potentialities. These potentialities coexist in a state of uncertainty until they are measured, and once they are measured, they collapse into a definite reality. This shift in perspective changes the very foundation of how we think about everything from subatomic particles to the universe as a whole. This uncertainty also extends beyond the behavior of particles. In quantum mechanics, the uncertainty principle, formulated by Werner Heisenberg, posits that it is impossible to simultaneously know both the position and momentum of a particle with perfect accuracy. The more precisely we measure one property, the less precisely we can know the other. This uncertainty is not just a limitation of measurement, but an intrinsic feature of nature. It suggests that, at the quantum level, there is no such thing as absolute knowledge or certainty about the state of a system. Everything exists in a state of potential, constantly fluctuating and evolving, waiting for observation to force it into a specific reality. Schrödinger's famous thought experiment involving the cat in the box illustrates these concepts in a striking and paradoxical way. The thought experiment imagines a scenario where a cat is placed inside a box with a device that has a 50% chance of killing the cat based on the decay of a radioactive atom. According to quantum mechanics, until the box is opened and the system is observed, the cat is both alive and dead at the same time, existing in a superposition of states. The cat's life and death are not distinct, separate realities, but probabilities that exist together in an indeterminate state. It is only through observation that one of these possibilities becomes real. This paradox is not meant to be taken literally, but rather serves to highlight the strange and counterintuitive nature of quantum reality, where multiple outcomes can coexist in a superposition until they are observed. Schrödinger's cat raises critical questions about the nature of measurement and observation in quantum mechanics. If reality is only determined by observation, then what role do we, as conscious beings, play in shaping the world around us? The act of observation seems to collapse the wave of probabilities into a single reality, suggesting that the observer plays a central role in the unfolding of events. This idea has led to deep philosophical debates about the nature of consciousness, the mind, and the universe. Some have argued that consciousness itself is fundamental to the process of measurement, implying that the mind and the physical world are interconnected in ways we have yet to fully understand. As we continue to explore the dual nature of reality, it becomes increasingly clear that the quantum world is far stranger and more mysterious than we ever could have imagined. It defies our classical intuitions, forcing us to confront the limits of human perception and understanding. Yet, as we delve deeper into this strange realm, we are also reminded that our imagination is as powerful a tool as our intellect. Schrödinger's mind, guided by both scientific rigor and philosophical curiosity, led us to new ways of thinking about the world, a world where possibilities are as real as actualities and where the very nature of existence is tied to the observer's perception. The dual nature of reality, once a baffling paradox, has become one of the most profound and transformative ideas in the history of science, shaping not only our understanding of the universe, but also the way we view ourselves within it. The implications of quantum mechanics, particularly the dual nature of reality, continue to resonate across various fields of study, far beyond the confines of physics. In fact, quantum mechanics has sparked a profound philosophical discussion on the nature of reality itself, challenging traditional metaphysical concepts and provoking questions that touch on the very fabric of existence. Schrödinger's wave-particle duality reveals that the physical world, at its most fundamental level, behaves in ways that we cannot directly observe or even fully comprehend with our human senses. The classical distinctions that have long guided our understanding of the universe are simply not adequate to explain what happens at the quantum scale. This realization prompts the consideration of a far more complex understanding of the universe, one in which everything is in flux, with the potential for countless outcomes existing simultaneously until a specific event occurs to crystallize one of those possibilities. The quantum world is, in essence, a dynamic network of probabilities, a space where things are neither fully definite nor entirely random but occupy a state of indeterminacy. As Schrödinger himself reflected, this brings us to question whether we can truly know anything with certainty. If particles, atoms, and even light can exist in states that are both defined and undefined at the same time, how can we assert that anything in our macroscopic world is completely fixed? Schrödinger's theoretical work has had far-reaching implications not only in physics but also in the realm of metaphysics and the philosophy of mind. The philosopher Immanuel Kant once posited that the reality we perceive is shaped by our senses and minds, which mediate our experience of the world. Quantum mechanics, in its strange and paradoxical nature, echoes this insight, suggesting that the observer, whether a human or a measurement device, somehow contributes to the realization of reality. This brings us to the idea of the observer effect, a phenomenon in quantum mechanics where the act of measurement alters the state of what is being measured. The question arises, to what extent does our consciousness play a role in shaping the world around us? Are we merely passive observers of a pre-existing reality, or are we actively involved in bringing that reality into being? Schrödinger's dual nature of reality, where particles can act as both waves and particles, forces us to rethink how we interact with the universe. It suggests that reality is not just something external to us, something we passively observe, but something that is created, in part, by our consciousness. This might seem like an outlandish philosophical idea, but the implications of quantum mechanics point to this very possibility. The mysterious act of measurement, where the superposition of possibilities collapses into a single reality, hints that the role of the observer is far more central than we might have imagined. The quantum observer, in this case, is not simply a passive entity observing a pre-existing reality, but a dynamic participant, actively contributing to the unfolding of events. This brings us to the deeper implications of the quantum world for our everyday lives. If particles exist in multiple states at once, this suggests that we, too, are connected to a broader, more complex web of possibilities than we might have imagined. Every moment of our lives is surrounded by an infinite number of potential outcomes, yet we experience just one. Quantum mechanics, then, challenges us to think about our own existence in new ways. Just as particles are not fixed entities but rather waves of potential that manifest into reality, our lives, too, may not be determined by a single, linear path. We are constantly interacting with a universe of possibilities, and our choices, our observations, play a role in shaping the reality that we experience. The idea of multiple possibilities, coexisting and fluctuating until observation forces them into a definite state, has profound implications for the way we view time and space. In the classical view, time is linear, and events follow a fixed order. However, quantum mechanics suggests that time, too, may not be as fixed as we imagine. The behavior of particles in a quantum system, which are subject to probabilistic laws, hints that time itself could be more flexible, with events unfolding in ways that are not entirely predictable. The concept of multiple, simultaneous possibilities existing at once calls into question the idea of a single, linear progression of time. Could it be that time, like everything else in the quantum world, is a fluid concept, subject to change and interpretation depending on how we observe it? As quantum theory has developed, it has led to the growth of new fields, such as quantum computing, which seeks to harness the principles of quantum mechanics to process information in radically different ways. Quantum computers exploit the properties of quantum bits, or qubits, which, unlike classical bits that can be in one of two states, 0 or 1, can exist in a superposition of both states simultaneously. This ability to exist in multiple states at once means that quantum computers can perform certain calculations much more efficiently than traditional computers. The power of quantum computing lies in the dual nature of reality, its ability to process information as both a particle and a wave, simultaneously calculating vast amounts of possibilities before collapsing them into a single solution. This is a powerful illustration of how the principles of quantum mechanics are beginning to have practical applications, extending beyond theoretical physics into the realm of technology. The wave-particle duality also has important implications for our understanding of light. Historically, light was thought to be either a wave or a particle, depending on the type of experiment conducted. In the 20th century, Einstein's explanation of the photoelectric effect demonstrated that light can behave as both a wave and a particle, depending on how it is observed. This idea, known as wave-particle duality, has become one of the cornerstones of quantum mechanics. It forces us to reconsider the very nature of light and, by extension, the nature of reality itself. If light can be both a wave and a particle, then what does this mean for the world we experience through our senses? Can we truly trust our perceptions of the world, or is reality much more malleable than we realize? Quantum mechanics, with its wave-particle duality, has also had a profound influence on our understanding of the fundamental forces that govern the universe. The fundamental forces, gravitational, electromagnetic, strong nuclear, and weak nuclear, are the forces that govern the interactions of matter and energy in the universe. These forces, although distinct in their properties, are unified in the quantum world, where they interact in ways that are not fully understood. Quantum mechanics has led to the development of quantum field theory, which attempts to describe these forces as fields that pervade the entire universe, with particles acting as excitations of these fields. This field-based understanding of the forces of nature presents a picture of the universe as an interconnected, dynamic whole, rather than a collection of isolated objects interacting with one another. Schrödinger's dual nature of reality forces us to acknowledge that the universe is not a static, fixed place, but a dynamic system in constant motion, governed by probabilities and uncertainties. The more we explore the quantum world, the more we realize that our classical understanding of reality is limited. Particles are not solid, predictable objects but wave-like entities that exist in multiple states at once. Time is not a simple, linear progression but a more fluid concept that can be influenced by observation, Our consciousness is not merely an observer of a pre-existing world, but an active participant in shaping the reality we experience. The dual nature of reality, as revealed through Schrödinger's work, forces us to reconsider the very foundations of how we understand the universe. It challenges us to accept the possibility that the world is far more mysterious, complex, and interconnected than we have ever imagined, a world where the boundaries between what is real and what is possible are not fixed but constantly in flux. In the early 20th century, the scientific community found itself standing on the precipice of a new era in understanding the nature of the universe. At the heart of this revolution was quantum mechanics, a field of physics that fundamentally challenged classical ideas of determinism and predictability. Among the scientists who played a pivotal role in shaping the development of quantum theory was Erwin Schrödinger, an Austrian physicist whose contributions not only transformed the field, but also left a lasting impact on how we perceive the physical world. Before Schrödinger's work, the world of subatomic particles was largely governed by classical mechanics, which operated on the assumption that particles followed predictable paths dictated by well-defined laws of motion. However, as scientists began to explore the behavior of particles at the atomic and subatomic levels, they encountered phenomena that defied classical explanations. The most notable of these was the mysterious nature of light and the behavior of electrons. The famous experiments conducted by scientists such as Albert Einstein and Niels Bohr had already shown that light exhibited both particle-like and wave-like properties, a concept that was radically different from anything classical physics had ever suggested. Schrödinger's major contribution to quantum mechanics was his development of wave mechanics, a mathematical framework that described how quantum particles, such as electrons, could behave as both particles and waves. This was a monumental shift from the earlier ideas of quantum theory, which were largely based on particle descriptions. Schrödinger's wave equation, which he formulated in 1925, became a cornerstone of quantum mechanics and provided a new, powerful way to predict the behavior of particles. Unlike the classical approach, which treated particles as discrete, localized objects with definite positions and velocities, Schrödinger's equation viewed particles as existing in wave-like states, with probabilities of being found in various locations. These states were described by a wave function, a mathematical function that encapsulated all of the possible positions, energies, and other properties of a quantum system. The wave equation Schrödinger developed was not merely a theoretical construct. It had profound implications for how we understand the behavior of particles. One of the most important insights to emerge from Schrödinger's work was the realization that particles do not have definite positions or velocities until they are measured. Instead, they exist as a cloud of probabilities, with different possibilities for their location and state. The wave function that Schrödinger introduced described the likelihood of finding a particle in a given state, and the act of measurement, according to quantum theory, would collapse this wave of possibilities into a single reality. This insight was both mind-bending and revolutionary, as it suggested that the universe, at its most fundamental level, is not a deterministic system but one governed by probabilities and uncertainties. Schrödinger's wave equation was instrumental in explaining the behavior of atoms and molecules. The electron, for example, was understood to orbit the nucleus in fixed energy levels, but Schrödinger's work showed that instead of orbiting in discrete paths, electrons exist in regions of space where they are most likely to be found, described by a wave function. This model was a departure from earlier models, such as Niels Bohr's planetary model, which depicted electrons as traveling in specific orbits. Schrödinger's wave mechanics offered a more accurate representation of the electron's behavior and provided a deeper understanding of atomic structure. One of Schrödinger's most famous contributions to quantum mechanics was his thought experiment known as Schrödinger's cat. This experiment, which was designed to illustrate the paradoxes inherent in quantum theory, involved placing a cat in a box with a radioactive atom. The atom had a 50% chance of decaying, which would release radiation that would trigger the death of the cat. If the atom did not decay, the cat would remain alive. According to quantum mechanics, the atom would be in a superposition of both decayed and undecayed states until it was observed, and as a result, the cat would also be in a superposition of being both alive and dead. This paradox highlighted the strange and counterintuitive nature of quantum mechanics, where particles and even macroscopic objects, in theory, could exist in multiple states at once. While Schrödinger's cat was not meant to be taken literally, it became an iconic symbol of the conceptual difficulties posed by quantum theory and the limits of our understanding of reality. Schrödinger's wave mechanics also laid the foundation for the development of quantum chemistry. By applying his wave equation to the behavior of atoms and molecules, scientists were able to explain chemical reactions, the formation of bonds, and the properties of elements in a way that was previously impossible. Schrödinger's work contributed to the understanding of molecular orbitals, electron configuration, and the behavior of atoms in chemical reactions, which had profound implications for fields such as materials science, nanotechnology, and molecular biology. Schrödinger's contributions were not just limited to the realm of theoretical physics. His work extended into the philosophical domain, where he became deeply engaged with questions about the nature of reality, observation, and consciousness. Schrödinger was keenly aware of the philosophical implications of his work and often wrote about the metaphysical questions that quantum mechanics raised. He was particularly interested in the relationship between mind and matter and how the act of observation could influence the state of a physical system. Schrödinger's views on consciousness and the nature of reality have been the subject of much debate and exploration in the years since his death. His writings continue to inspire those interested in the intersection of science and philosophy, especially in the fields of consciousness studies and the philosophy of mind. In addition to his work in quantum mechanics, Schrödinger was also deeply interested in the study of biological systems and the origins of life. He wrote a famous book, What is Life?, in which he explored the relationship between physics, biology, and the nature of life itself. In this work, Schrödinger speculated about the molecular basis of life and introduced the concept of a genetic code long before the discovery of DNA. His ideas were influential in shaping the direction of biological research and provided a foundation for the development of molecular biology and genetics. Schrödinger's impact on quantum mechanics cannot be overstated. His wave equation provided a crucial framework for understanding the behavior of particles, and his work has influenced generations of physicists, chemists, and philosophers. Schrödinger's ideas have been validated and expanded upon by subsequent discoveries in quantum mechanics, including the development of quantum field theory and quantum computing. His contributions laid the groundwork for modern physics and have had far-reaching implications for our understanding of the universe. Schrödinger's work also paved the way for the development of technologies that are now integral to our daily lives. Quantum mechanics, the very field Schrödinger helped shape, is the foundation for technologies such as lasers, semiconductors, and computers. The principles of quantum mechanics, including wave-particle duality and superposition, are harnessed in quantum computing, which promises to revolutionize fields such as cryptography, medicine, and artificial intelligence. Schrödinger's work has thus played a central role in shaping the technological landscape of the modern world. While Schrödinger's contributions to quantum mechanics have been immeasurable, it is important to remember that his work was not completed in isolation. He was part of a vibrant scientific community that included physicists like Niels Bohr, Albert Einstein, and Werner Heisenberg, all of whom contributed to the development of quantum theory. Schrödinger's work built upon the foundations laid by these pioneers and in turn, his ideas have influenced the work of physicists today. The development of quantum mechanics was a collaborative effort, and Schrödinger's contributions were a vital piece of the puzzle that has helped unlock the mysteries of the quantum world. In the years following Schrödinger's death in 1961, his work continued to inspire generations of scientists, and his name became synonymous with the revolutionary ideas that reshaped our understanding of reality. Today, Schrödinger is remembered not only as one of the giants of quantum mechanics, but also as a thinker whose contributions to science extended beyond the realm of physics and into the domain of philosophy, biology, and even the search for the meaning of life itself. Schrödinger's legacy lives on in the continued exploration of the quantum world, and in the many ways his ideas have influenced modern science and technology. His work continues to shape our understanding of the universe and remains a testament to the power of human imagination and intellect. Schrödinger's contributions to quantum mechanics are a cornerstone of modern physics, and his influence on the development of quantum theory will be felt for generations to come. Schrödinger's contributions to quantum mechanics were not just theoretical achievements, they were transformative moments that fundamentally altered the way we perceive the universe and our place within it. His work on the wave equation and the development of wave mechanics brought clarity to the confusing, often paradoxical world of quantum theory. Yet, as significant as his scientific achievements were, Schrödinger's exploration of the deeper philosophical implications of quantum mechanics is equally notable. In understanding his legacy, we must not only consider his mathematical innovations but also how his thinking bridged the gap between physics and philosophy, leaving an indelible mark on both fields. One of the critical aspects of Schrödinger's legacy is his equation, which serves as the mathematical foundation for much of modern quantum theory. The Schrödinger equation, in its simplest form, describes how the quantum state of a physical system changes over time. Schrödinger's insight was that instead of treating particles as discrete points moving in deterministic ways, particles should be viewed as existing in a cloud of probabilities, represented by a wave function. The wave function contains all the information about the system and can be used to calculate the probability of finding a particle in a specific state. This probabilistic nature of particles at the quantum level was a direct challenge to classical physics, which was based on the deterministic ideas of Isaac Newton. In classical physics, the future state of a system could be predicted with absolute certainty if its initial conditions were known. But in quantum mechanics, this certainty is replaced by probability, a reality that is, in many ways, more in line with the unpredictable nature of the universe itself. The wave equation is not only an elegant mathematical tool but a window into the strange and mysterious world of quantum mechanics. Schrödinger's equation revolutionized our understanding of atomic and subatomic systems, allowing scientists to explain the behavior of electrons in atoms and molecules with greater precision. Before Schrödinger, the behavior of atoms was largely described by models based on classical physics, such as the Bohr model of the atom, which depicted electrons orbiting the nucleus in fixed paths. Schrödinger's wave mechanics, however, replaced these fixed orbits with probability clouds, giving rise to the modern concept of atomic orbitals. These orbitals are regions of space where electrons are most likely to be found, and they are not fixed paths but rather fluctuating areas of probability. Schrödinger's work made it possible to understand the arrangement of electrons in atoms, the formation of chemical bonds, and the nature of chemical reactions in a fundamentally new way. Beyond the practical implications of his wave equation, Schrödinger's ideas also sparked a profound philosophical inquiry into the nature of reality itself. One of the most famous and most debated elements of Schrödinger's work is his thought experiment, the Schrödinger's cat paradox. The paradox involves a cat in a box that is simultaneously alive and dead based on the quantum state of a radioactive atom inside the box. The cat's fate is linked to the decay of the atom, and according to quantum mechanics, until the box is opened and the system is observed, the cat exists in a superposition of both states alive and dead. This paradox is a powerful illustration of the strangeness of quantum mechanics, where particles, and even macroscopic objects, in theory, can exist in multiple states at once. The Schrödinger's cat experiment was designed to highlight the absurdity of applying quantum principles to everyday objects, but it also raises deeper questions about the role of the observer in determining the nature of reality. The paradox suggests that the act of observation, or measurement, plays a central role in the unfolding of events in the quantum world. Before the system is observed, all possibilities exist simultaneously. But once the system is measured, the wave of probabilities collapses into a single reality. In the case of Schrödinger's cat, the cat is either alive or dead only when the box is opened and the state is observed. The concept of wave function collapse has profound implications for how we think about the nature of reality itself. If the act of measurement determines the state of a system, then what role does the observer play in the creation of reality? This question has led to philosophical debates about the nature of consciousness, with some suggesting that consciousness itself may be necessary to collapse the wave function and bring reality into existence. Schrödinger himself was deeply concerned with the philosophical implications of his work, and he often expressed skepticism about the idea that consciousness could be tied so directly to the physical world. He believed that quantum mechanics, as revolutionary as it was, could not fully explain the nature of consciousness. In addition to his work on quantum mechanics, Schrödinger's contributions to biology were equally groundbreaking. In his famous book What is Life, published in 1944, Schrödinger explored the connection between physics and biology and offered insights into the molecular basis of life. Although this work was not widely recognized at the time, it laid the foundation for the development of molecular biology and genetics. Schrödinger proposed that the physical processes of life could be explained by the principles of quantum mechanics, particularly in terms of how genetic information is stored and transmitted. He speculated that the genetic code was encoded in a molecule that carried the instructions for building and maintaining an organism. Schrödinger's insights were prescient, as they anticipated the later discovery of the structure of DNA and the development of molecular genetics. His work demonstrated that the principles of physics were not confined to the study of matter and energy alone, but were equally applicable to the study of life itself. Schrödinger's ability to bridge the gap between physics and biology was a testament to his intellectual versatility and his broad view of science. He was not content to limit his thinking to one area of inquiry. Instead, he sought to understand the interconnectedness of all things. This holistic approach to science influenced not only his work in physics but also his philosophy and his views on the nature of life. Schrödinger believed that the search for truth in science was not just about finding answers to specific problems, but about understanding the deeper, unifying principles that governed all aspects of existence. In this sense, Schrödinger's contributions to science were as much about the philosophy of science as they were about physics and biology. He was deeply concerned with how scientific discoveries shaped our understanding of the world and how they could be used to answer the most profound questions about the nature of life, consciousness, and reality. Schrödinger's work laid the groundwork for many of the advances in quantum theory that would follow. His wave equation provided a framework for understanding the behavior of particles at the quantum level, and his contributions to molecular biology inspired a new generation of researchers to explore the molecular mechanisms underlying life. Schrödinger's philosophical reflections on quantum mechanics, meanwhile, continue to shape debates about the nature of reality and the role of the observer in the process of measurement. As quantum mechanics has advanced in the decades since Schrödinger's time, many of his ideas have been tested, refined, and expanded upon. The development of quantum field theory, quantum computing, and other areas of modern physics has been built on the foundations laid by Schrödinger and his contemporaries. Yet, despite the many advances in our understanding of the quantum world, the fundamental mysteries that Schrödinger helped to uncover remain as puzzling as ever. The dual nature of reality, as revealed by quantum mechanics, continues to challenge our intuitions and force us to rethink our basic assumptions about the universe. Schrödinger's work has left an indelible mark on the field of physics, and his contributions continue to shape the course of scientific inquiry. In conclusion, Schrödinger's legacy is one of intellectual breadth and depth, combining groundbreaking scientific discoveries with a profound engagement with the philosophical questions that arise from those discoveries. His work in quantum mechanics, molecular biology, and the philosophy of science has had a lasting impact on the scientific community, and his influence extends far beyond the field of physics. Schrödinger's contributions to our understanding of the universe are as relevant today as they were when he first made them, and his legacy will continue to inspire generations of scientists, philosophers, and thinkers for years to come. Erwin Schrödinger's thought experiment, commonly known as Schrödinger's cat, stands as one of the most profound and paradoxical illustrations of the strange world of quantum mechanics. While Schrödinger did not intend for the cat experiment to be taken literally, it serves as a crucial tool in helping us grapple with the core mysteries of quantum theory, mysteries that challenge our understanding of reality, observation, and existence. The paradox lies at the intersection of science and philosophy, leading us to confront some of the deepest questions about how the universe works at the most fundamental level. The concept of Schrödinger's cat emerges from the principles of quantum mechanics, a field of physics that asserts that particles do not have definite properties or states until they are measured. In the classical world, objects have clear, well-defined positions and states of being. A chair is either present or absent. A ball is either rolling or stationary. However, in quantum mechanics, particles exist in a state of superposition where they can be in multiple states at once, and only when they are observed does their state collapse into a single reality. Schrödinger's cat was designed to illustrate this strange and counterintuitive nature of quantum mechanics. In the thought experiment, Schrödinger imagines a cat enclosed in a box with a device that includes a radioactive atom. The atom has a 50% chance of decaying, and if it does, it triggers the release of poison that kills the cat. If the atom does not decay, the cat remains alive. According to quantum mechanics, the atom is in a superposition of both decayed and undecayed states until it is observed. By extension, the cat is simultaneously alive and dead, both existing in a superposition of states until the box is opened and the system is observed. This scenario is, of course, paradoxical from the perspective of everyday experience, where the cat is either alive or dead, but never both at once. The thought experiment serves to highlight the absurdity of applying quantum mechanics to macroscopic objects large enough for us to perceive clearly, like cats. At its core, Schrödinger's cat challenges our fundamental understanding of observation and reality. In quantum mechanics, the act of measurement plays a pivotal role in determining the state of a system. A particle exists in a superposition of possibilities, each corresponding to a different state, and it is only through measurement or observation that one of these possibilities collapses into a definitive reality. This idea, known as the wave function collapse, suggests that before observation, all states are possible. Once the system is observed, however, the wave of possibilities collapses into a single state. This is often referred to as the observer effect. In the case of Schrödinger's cat, the cat exists in a superposition of being both alive and dead, and it is only the act of opening the box and observing the cat that forces it into one state or the other. This paradox raises profound philosophical questions about the nature of reality itself. If the act of observation determines the state of a quantum system, then does this imply that reality is not fixed until it is observed? Are we, as observers, creating the reality we perceive? And what does it mean for something to be real if it exists in multiple possibilities until it is observed? Schrödinger's cat invites us to reconsider the very nature of existence, suggesting that reality is not a set of fixed, predetermined events, but a collection of probabilities that unfold as we interact with them. These questions are not merely theoretical. Schrödinger's thought experiment has profound implications for how we understand the nature of consciousness and the role of the observer in shaping the world. Some interpretations of quantum mechanics, such as the Copenhagen interpretation, suggest that consciousness itself may be a necessary component in the measurement process. In this view, it is the conscious observer who collapses the wave function, bringing a definite state into existence. This idea raises intriguing questions about the relationship between mind and matter, suggesting that consciousness may not be a passive observer of the universe, but an active participant in the unfolding of reality. If consciousness plays a central role in the creation of reality, then our thoughts, perceptions, and observations may have a direct impact on the physical world around us. These philosophical questions were not lost on Schrödinger himself. In fact, he was deeply concerned about the implications of quantum mechanics for our understanding of reality. While he made profound contributions to the development of quantum theory, Schrödinger was also skeptical about the idea that consciousness could be so closely tied to the physical world. In his later years, he expressed discomfort with the idea that the mind could collapse the wave function and bring about physical reality. For Schrödinger, quantum mechanics was a tool for understanding the behavior of particles at the atomic level, but he was not convinced that it offered a complete or satisfying explanation of the nature of consciousness. Nonetheless, his paradox continues to provoke debate and inquiry in the scientific and philosophical communities. Schrödinger's cat is not just a metaphor for the strange behavior of quantum particles. It is a symbol of the uncertainty and indeterminacy that lies at the heart of quantum mechanics. The paradox forces us to confront the limits of human knowledge and perception. In the quantum world, things are not as they appear. Particles do not have definite properties until they are observed. Instead, they exist in a state of potential, constantly fluctuating between different possibilities. This is a stark departure from the classical view of the universe, in which the world operates according to fixed laws that govern all events with certainty. The quantum world is one of probability, uncertainty, and interconnectedness, where multiple outcomes coexist until an observation brings them into focus. As we move forward in our exploration of quantum mechanics, Schrödinger's cat continues to serve as a powerful reminder of the limitations of human perception and the strangeness of the universe. The paradox has inspired generations of scientists, philosophers, and thinkers to question the very nature of reality and to explore the role of observation, measurement, and consciousness in the process of creation. Schrödinger's cat may remain a paradox, but it is also an invitation to rethink our assumptions about the world and our place within it. Beyond the realm of quantum mechanics, Schrödinger's cat has also had an impact on the broader cultural imagination. The thought experiment has been used in literature, art, and popular culture to explore themes of uncertainty, duality, and the limits of human understanding. It has become a symbol of the tension between what we know and what we cannot know, the space between the possible and the actual. Schrödinger's cat serves as a powerful metaphor for the mysteries of the universe, a reminder that there is much about the world that remains beyond our grasp. In conclusion, Schrödinger's cat is much more than a thought experiment in quantum mechanics. It is a profound and paradoxical illustration of the fundamental nature of reality, observation, and existence. The experiment challenges our understanding of the world, forcing us to reconsider the role of the observer in shaping the reality we experience. It asks deep questions about the relationship between mind and matter and suggests that reality may not be as fixed as we once believed. Schrödinger's cat is a powerful symbol of the uncertainty and indeterminacy at the heart of the quantum world, and it continues to provoke thought and debate in the fields of science and philosophy. It serves as a reminder that the universe is not as we perceive it, and that the more we learn, the more we realize just how little we truly know. Schrödinger's cat continues to have a profound impact not only in the scientific community but in various other domains such as philosophy, art, and popular culture. The paradox forces us to confront the deeply uncertain nature of the universe at its most fundamental level. By posing such a bizarre scenario, where a cat could be alive and dead at the same time, Schrödinger opened up a floodgate of questions about the very structure of reality and the limits of human understanding. While Schrödinger's original intention was to critique the strange consequences of quantum mechanics and highlight the absurdity of applying its principles to macroscopic objects, the implications of the thought experiment reverberated beyond physics into the realms of metaphysics, epistemology, and even psychology. One of the most profound impacts of Schrödinger's cat is on how we understand the relationship between the observer and the observed. In quantum mechanics, the observer plays a central role in determining the state of a system. The so-called observer effect suggests that the act of measurement itself causes the wave function, the mathematical description of all possible states, to collapse into a single reality. This idea contradicts classical notions where an object's properties exist independently of observation. In the quantum world, however, reality does not exist in a definite state until it is measured. Schrödinger's cat, as an extension of this concept, forces us to ask, what happens when we are not observing? Does reality itself become fluid, and is it only through our act of observation that the universe solidifies into the form we experience? Schrödinger's cat also invites us to reconsider the very nature of existence. If reality is dependent on observation, as quantum mechanics suggests, then how do we define what is real? The paradox challenges us to think about the notion of existence itself, blurring the lines between what is actual and what is merely potential. If the cat exists both alive and dead until the box is opened, then perhaps we, too, exist in multiple states at once, our lives unfolding according to multiple, simultaneous possibilities. This brings us to a point where science, philosophy, and even mysticism intersect. The idea that multiple realities can exist simultaneously forces us to contemplate the nature of free will, fate, and the choices that we make. The philosophical implications of Schrödinger's cat have been explored extensively by thinkers from a wide variety of fields. In the 20th century, quantum mechanics introduced an entirely new paradigm for understanding reality, one that sharply contrasts with the deterministic worldview of classical physics. If, as quantum theory suggests, events are not strictly determined and can unfold in a multiplicity of ways, then the world is far less predictable and more contingent than we ever imagined. Some philosophers, particularly those influenced by existentialism, have used Schrödinger's cat to argue that we live in a world of profound uncertainty, one where our perceptions shape the reality we experience. This uncertainty lies at the core of human existence, and much like the cat in Schrödinger's thought experiment, our lives may be simultaneously filled with endless possibilities until we choose a particular path. In this way, Schrödinger's cat represents not just a scientific problem, but an existential question about how we understand choice, observation, and reality itself. The observer is no longer a passive entity that simply looks at the world. The observer is active, shaping the world through their attention. This concept of the active observer aligns with ideas in philosophy and even psychology, where the subject's perceptions and interpretations of the world are seen as constitutive of their reality. In this view, the observer does not just watch the unfolding of events. Their consciousness plays a role in bringing those events into being. This view is echoed in the field of quantum consciousness, where some researchers suggest that the mind itself could play a crucial role in determining the outcome of quantum processes. Schrödinger's thought experiment thus raises significant questions about the nature of consciousness, the mind, and how we engage with the world. Beyond its influence on philosophy, Schrödinger's cat has become an enduring cultural symbol. The paradox has captured the public imagination, not just in scientific circles but in the arts, literature, and popular culture. Its central theme of duality, of being both alive and dead, of existing in two states at once, has resonated with broader cultural concerns about identity, existence, and choice. Schrödinger's cat embodies the struggle between the known and the unknown, certainty and uncertainty, offering a metaphor for the human condition itself. The idea that one can exist in multiple states of being simultaneously reflects the complexities of modern life, where individuals often feel torn between competing desires, responsibilities, and aspects of their identity. In literature and cinema, Schrödinger's cat has appeared as a symbol of uncertainty and existential paradox. The concept of being in two places at once, or in two states simultaneously, mirrors the struggles of characters caught between different worlds or realities. The concept of a dual existence, of being simultaneously alive and dead, has been explored in various works of fiction, often serving as a metaphor for characters who must reconcile conflicting parts of themselves or navigate the tension between fate and free will. The paradoxical nature of the cat serves as an elegant and thought-provoking way to explore deeper psychological themes, from the fragility of identity to the nature of choice and agency. Schrödinger's cat also serves as a cultural touchstone for discussing the limitations of human perception and the potential for new ways of seeing the world. Just as quantum mechanics challenges our understanding of the physical universe, Schrödinger's cat asks us to reconsider the limits of human knowledge and understanding. The paradox suggests that our perception of reality is not as absolute as we might think. Our senses provide us with only a partial view of the universe, one that is shaped by our subjective experience. Schrödinger's cat encourages us to accept that there is much more to the universe than we can perceive, and that the true nature of reality may be far stranger and more complex than we can imagine. In contemporary discussions about science and technology, Schrödinger's cat continues to provoke debates about the implications of quantum theory for our understanding of reality. As modern physics moves into new and increasingly abstract realms, Schrödinger's cat remains a symbol of the mysteries that quantum mechanics continues to present. It serves as a reminder that the boundaries between the observable and the unobservable, the knowable and the unknowable, are not as fixed as we once believed. Quantum mechanics, as Schrödinger demonstrated, forces us to question everything we thought we knew about the nature of the universe. The very act of observing, the very act of measuring, brings about the reality we experience. But what does this say about our place in the universe? Are we mere observers, or do we play an active role in shaping the world around us? One of the most intriguing consequences of Schrödinger's cat is its potential to blur the line between science and spirituality. For centuries, science and religion, or spirituality, have been viewed as two opposing forces, each with its own framework for understanding the universe. However, as quantum mechanics forces us to confront the uncertainty and mystery of the world, it also opens the door to deeper questions about the nature of consciousness, existence, and the interconnectedness of all things. Schrödinger's cat, as a metaphor for duality and the limits of perception, speaks to a broader human desire to understand the nature of the universe, not just through empirical science, but through the lens of spiritual insight. It forces us to confront the possibility that the universe, in its deepest essence, may be something far greater and more interconnected than we can fully grasp. Schrödinger's cat will always remain a cornerstone of quantum mechanics, a paradox that highlights the strange and mysterious behavior of the quantum world. But its implications extend far beyond the confines of physics, sparking philosophical inquiries into the nature of reality, the role of the observer, and the limits of human knowledge. The cat may remain alive and dead, simultaneously occupying two states, but in doing so, it challenges us to rethink what we know about existence itself. In the end, Schrödinger's cat is not just a thought experiment in physics, but a profound and timeless symbol of the uncertainty, complexity, and beauty of the universe. Quantum superposition is a principle at the core of quantum mechanics, describing a phenomenon where a particle exists in multiple states simultaneously until it is measured or observed. This mind-boggling concept challenges our classical understanding of reality, which relies on the assumption that objects have definite properties at all times. Superposition, however, defies this notion by allowing particles to occupy more than one state at once, existing in a superposition of multiple possible outcomes. In its simplest form, quantum superposition suggests that until we observe or measure a quantum system, its properties do not have fixed values. Instead, they are described as a range of probabilities. For example, an electron does not have a well-defined position in space until we measure it. Rather, it exists as a probability wave, spreading out across a region. This concept is elegantly illustrated in Schrödinger's thought experiment with his famous cat paradox. The cat, in this scenario, is both alive and dead, existing in a superposition of these two states until the box is opened and the system is observed. It's an outcome of the strange, probabilistic nature of quantum particles, where all possibilities can coexist simultaneously. This idea stretches our imagination, opening doors to new ways of thinking about the universe. The quantum world is not a place of certainty and fixed outcomes, but a realm of possibility, where the potential for various outcomes exists in parallel until observed. It introduces the idea that reality itself may not be as objective as we once thought. Rather, it may be subject to the observer's interaction, where the act of measurement collapses a range of possibilities into a single, concrete reality. This concept parallels philosophical ideas in which the observer is seen as a creator or shaper of the reality they perceive. Quantum superposition challenges the very fabric of how we experience the world, prompting us to rethink the relationship between consciousness and the material universe. The implications of quantum superposition extend beyond the confines of physics, sparking creative exploration in various fields. In art, literature, and philosophy, the notion of multiple possibilities existing simultaneously serves as a metaphor for the complexity and uncertainty of life. Just as a particle can exist in multiple states, human existence can be seen as a collection of potentialities, multiple paths that one can take, each leading to a different outcome. Quantum superposition invites us to consider the complexity of human choice and the unpredictable nature of the world around us. In the world of imagination, the concept of superposition has the power to revolutionize how we think about creativity. If reality can exist as a series of potential outcomes, then perhaps our thoughts, dreams, and aspirations operate similarly in a state of possibility. Imagination itself may be an extension of this quantum process, where ideas are not bound by the limitations of physical reality, but instead exist in a vast field of probabilities. The creative process, much like the quantum world, involves exploring various possibilities and letting those ideas exist in a fluid, non-fixed state until they are brought into reality through action and observation. The connection between quantum mechanics and imagination lies in the infinite possibilities that exist before a choice is made, whether in the realm of scientific experimentation or creative expression. In a more practical sense, quantum superposition has been harnessed in the development of quantum computing. Quantum computers utilize qubits, which, like quantum particles, can exist in multiple states simultaneously. This allows them to perform complex calculations at incredible speeds, exploring multiple solutions at once. By embracing the principles of quantum superposition, quantum computers break through the limitations of classical computing, which relies on binary systems of 0 seconds and 1 second. Qubits, however, can represent both 0 and 1 at the same time, vastly expanding computational power and efficiency. As a result, quantum computing holds the potential to revolutionize fields ranging from cryptography to artificial intelligence, providing solutions to problems that are currently intractable for traditional computers. Ultimately, quantum superposition invites us to challenge the way we think about reality, creativity, and the universe itself. It pushes us to question our assumptions about certainty and introduces a world where multiple possibilities coexist and interact. Whether in science, art, or philosophy, superposition reveals a universe full of infinite potential, where the boundaries between what is possible and what is actual blur, and where the act of observation itself plays a key role in shaping the world we experience. The observer effect is a fundamental concept in quantum mechanics that underscores the profound role of the observer in shaping the reality of a quantum system. At its core, the observer effect suggests that the very act of observing a quantum system can influence its state. In classical physics, we are accustomed to thinking of the world as existing independently of our observation. Objects have definite properties, whether or not we look at them. However, in the quantum world, this assumption breaks down. Quantum particles, such as electrons or photons, exist in a superposition of multiple states simultaneously, with probabilities assigned to each state. When an observer measures a quantum system, the superposition collapses into one of these possible states. This phenomenon is best understood through experiments such as the double-slit experiment. In this experiment, particles like electrons are fired at a screen with 2 slits. If no one observes the particles as they pass through the slits, they behave as waves, creating an interference pattern on the other side. However, when a measurement is made to determine which slit the particle passes through, the interference pattern disappears, and the particles behave like discrete objects, creating 2 distinct patterns. This outcome suggests that the act of observation itself alters the behavior of the particles, forcing them into one state rather than allowing them to exist in multiple possibilities at once. The observer effect challenges our classical understanding of reality, in which the world is independent of our perceptions. Instead, it suggests that reality is not fixed until we interact with it, pointing to a deeply interconnected relationship between the observer and the observed. This raises profound questions about the nature of reality, consciousness, and the role of perception. If reality is shaped by observation, does this mean that our consciousness plays a fundamental role in the creation of the universe? Some interpretations of quantum mechanics, such as the Copenhagen interpretation, suggest that consciousness itself is required to collapse the wave function, turning possibilities into actualities. While this view has sparked debate, it has also encouraged a reconsideration of how we understand the universe and our place within it. The implications of the observer effect extend far beyond quantum physics. Philosophers have long debated the nature of reality and the role of perception in shaping the world around us. In light of the observer effect, these discussions take on a new urgency. If our observation has the power to influence the state of a quantum system, can we say that the world exists in an objective, fixed form, independent of our consciousness? Or is reality itself a fluid, ever-changing construct that depends on our engagement with it? These questions challenge not only our understanding of physics, but also the very nature of existence itself. The observer effect also has practical applications in the world of technology. Quantum computing, for instance, takes advantage of the strange properties of quantum systems, including superposition and entanglement. Qubits, the basic units of quantum information, can exist in multiple states simultaneously, vastly increasing computational power. However, the observer effect plays a critical role in quantum computing, as qubits must be measured to extract information. The act of measurement, however, collapses the superposition, forcing the qubit into a definite state. This interplay between measurement and collapse is a key challenge in developing quantum computers that can operate efficiently and reliably. Despite these challenges, quantum computing holds immense potential, with applications in cryptography, drug discovery, and artificial intelligence. The observer effect also invites us to rethink the nature of free will and the relationship between mind and matter. If our consciousness is indeed integral to shaping the reality we observe, then perhaps the act of observing is not a passive process but an active one. In this view, we are not simply witnesses to the unfolding of the universe, but participants in its creation. This perspective aligns with ideas in philosophy and psychology that suggest consciousness is not merely a byproduct of brain activity, but a fundamental aspect of reality itself. By actively engaging with the world, we may influence its outcome in ways that are not yet fully understood. In conclusion, the observer effect stands as one of the most fascinating and mysterious aspects of quantum mechanics, offering profound insights into the relationship between observation, reality, and consciousness. It challenges our traditional understanding of the universe as an independent, objective reality, and forces us to consider the possibility that we, as observers, play an integral role in shaping the world around us. Whether in the quantum realm or in our everyday lives, the observer effect invites us to rethink the very nature of existence and the power of perception in creating our reality. Throughout the history of human thought, science and philosophy have often been seen as two distinct realms, each with its own methods of inquiry and understanding of the world. Science is typically associated with empirical observation, experimentation, and the systematic study of the natural world, while philosophy concerns itself with questions of existence, knowledge, ethics, and the fundamental nature of reality. Despite their apparent differences, science and philosophy are deeply interconnected. The boundaries between the two fields have always been fluid, with each influencing and shaping the other in profound ways. At the heart of the intersection between science and philosophy is the quest for understanding the nature of reality. In many ways, science seeks to answer the how of the universe, the mechanisms, laws, and principles that govern the natural world. Philosophy, on the other hand, often seeks to answer the why, the deeper, more existential questions about the meaning and purpose of life, the nature of consciousness, and the limits of human knowledge. While science aims to uncover the workings of the universe, philosophy provides the conceptual frameworks and ethical considerations that guide scientific inquiry. This interconnection is particularly evident in the development of modern physics. The advent of quantum mechanics, for example, has had profound implications not only for science but also for philosophy. Quantum mechanics challenges our traditional notions of reality, introducing concepts such as superposition, entanglement, and wave-particle duality that defy our classical understanding of the world. These concepts have led to philosophical debates about the nature of existence, the role of the observer, and the limits of human perception. In many ways, the strange and counterintuitive nature of quantum mechanics has forced scientists and philosophers alike to reconsider their assumptions about the nature of reality. One of the most significant philosophical questions raised by quantum mechanics is the role of the observer in shaping reality. According to quantum theory, particles do not have definite properties until they are measured or observed. The act of observation causes a quantum system to collapse from a superposition of possible states into a single, definite state. This idea has led to philosophical discussions about the nature of consciousness and its relationship to the physical world. Some interpretations of quantum mechanics suggest that consciousness plays a central role in the measurement process, while others argue that the observer effect is merely a product of the limitations of measurement. Regardless of the interpretation, quantum mechanics has raised profound questions about the relationship between mind and matter and the role of perception in shaping the world around us. Philosophy also plays a crucial role in shaping the ethical considerations of scientific progress. As science continues to advance and produce new technologies, it is essential to ask ethical questions about their potential impact on society. Issues such as genetic engineering, artificial intelligence, and climate change require careful philosophical reflection on the consequences of scientific advancements. Philosophy provides the ethical frameworks that guide scientists in making decisions about how their discoveries should be applied. For example, the ethical dilemmas surrounding the use of genetic modification in humans or animals require deep philosophical discussions about the limits of human intervention in nature and the potential consequences of altering the fundamental building blocks of life. Furthermore, the relationship between science and philosophy is crucial in the realm of epistemology, the study of knowledge itself. Philosophy has long grappled with questions about the nature of knowledge, the limits of human understanding, and the reliability of our senses. These questions are at the core of scientific inquiry. The scientific method relies on observation, experimentation, and reasoning to uncover truths about the world, but it is always aware of the limitations of human perception and the potential for error. Philosophy provides the tools for questioning the assumptions that underlie scientific inquiry and for considering the nature of truth and knowledge. This dialogue between science and philosophy has led to some of the most important intellectual advancements in history, from the development of the scientific method to the rise of modern philosophy. In the modern era, the integration of science and philosophy has led to new fields of interdisciplinary study, such as the philosophy of science and the philosophy of mind. The philosophy of science examines the foundations, methods, and implications of scientific knowledge, while the philosophy of mind explores questions about consciousness, cognition, and the relationship between the brain and the mind. These fields of inquiry highlight the ongoing interplay between science and philosophy and underscore the importance of considering both perspectives when seeking to understand the nature of reality. The relationship between science and philosophy is also evident in the works of great thinkers like Albert Einstein, Niels Bohr, and Erwin Schrödinger. These scientists not only made groundbreaking contributions to the field of physics, but also engaged with philosophical questions about the nature of space, time, and reality. Einstein, for example, famously remarked that science without religion is lame, religion without science is blind, suggesting that both scientific inquiry and philosophical reflection are essential for understanding the universe. Schrödinger, too, was deeply concerned with the philosophical implications of his work in quantum mechanics, particularly in regard to the nature of consciousness and the role of the observer. The interconnection of science and philosophy is not limited to physics, however. In fields such as biology, psychology, and ethics, philosophical questions continue to shape the direction of scientific research. In biology, for example, the study of evolution has prompted debates about the nature of life and the meaning of human existence. In psychology, the study of the mind and consciousness raises questions about the nature of self-awareness and the relationship between the mind and the body. And in ethics, the advancement of medical science and biotechnology has led to ongoing discussions about the moral implications of scientific progress. In conclusion, the relationship between science and philosophy is one of mutual enrichment. While science seeks to uncover the workings of the natural world, philosophy provides the conceptual frameworks and ethical considerations that guide scientific inquiry. The intersection of these two fields has led to some of the most profound and transformative ideas in human history, and it continues to shape the way we understand the universe, ourselves, and our place within it. By fostering dialogue between science and philosophy, we are better equipped to confront the complex questions of existence, knowledge, and ethics that define the human experience. Erwin Schrödinger's legacy is deeply ingrained in the very fabric of modern physics, particularly in the domain of quantum mechanics. His pioneering contributions, particularly the development of wave mechanics and his formulation of the Schrödinger equation, revolutionized our understanding of atomic and subatomic particles. Schrödinger's work not only helped to lay the groundwork for the emerging field of quantum mechanics in the 20th century, but it also continues to influence scientific thought today. His legacy is multifaceted, encompassing both profound theoretical advancements in science and profound philosophical inquiries about the nature of reality, consciousness, and the role of observation in shaping the world we experience. At the heart of Schrödinger's legacy is his equation, which described the behavior of quantum particles using a wave function. Schrödinger's wave equation was a significant departure from classical physics, where particles were understood to follow fixed paths or trajectories. In Schrödinger's model, particles exist as probability waves, not as point-like objects. This idea of quantum particles being in a superposition of multiple states simultaneously was a radical shift in how scientists viewed the universe. The Schrödinger equation provided a mathematical framework for understanding the behavior of particles at the atomic and subatomic levels, offering predictions that have since been validated through experimental observation. Schrödinger's work on the wave equation was instrumental in the development of quantum mechanics as a discipline. Prior to Schrödinger's contribution, quantum mechanics was still in its infancy, with many aspects remaining unclear and undefined. Niels Bohr's atomic model had described electrons in fixed orbits around the nucleus, but Schrödinger's model expanded on this by incorporating the wave-like nature of particles. His contributions enabled a deeper understanding of phenomena like atomic spectra and electron behavior, and they played a key role in the development of quantum theory as we know it today. However, Schrödinger's legacy extends beyond his scientific work. It also touches on the philosophical questions that quantum mechanics raised. His famous thought experiment, Schrödinger's cat, illustrates the paradoxes inherent in quantum theory, particularly the concept of superposition. The idea that a cat in a sealed box could be both alive and dead at the same time challenges our intuitive understanding of reality. Schrödinger's cat serves as a metaphor for the strange behavior of quantum systems, where particles exist in multiple states simultaneously until they are observed. This paradox has had far-reaching philosophical implications, leading to debates about the nature of observation, consciousness, and the relationship between mind and matter. Schrödinger himself was deeply concerned with these philosophical questions and sought to understand the implications of quantum mechanics for our understanding of reality. In the years following Schrödinger's death, his work continued to inspire new generations of physicists and thinkers. His ideas laid the foundation for further developments in quantum mechanics, such as quantum field theory and quantum computing. In the mid-20th century, physicists like Richard Feynman and Paul Dirac expanded on Schrödinger's work, helping to refine our understanding of quantum systems. Quantum mechanics has since evolved into one of the most successful and experimentally verified theories in physics, with its predictions consistently matching observation in areas ranging from atomic structure to the behavior of particles and accelerators. Schrödinger's contributions also helped to shape the way we think about the future of quantum exploration. In recent years, quantum mechanics has found applications in areas such as quantum computing, cryptography, and quantum communication. The field of quantum computing, in particular, has the potential to revolutionize technology, offering the possibility of solving problems that are intractable for classical computers. Quantum computers exploit the principles of superposition and entanglement, allowing them to process vast amounts of information simultaneously and perform calculations exponentially faster than traditional computers. Schrödinger's work on wave mechanics and quantum states provides the theoretical foundation for this exciting new frontier in technology. Moreover, the future of quantum exploration is also being shaped by advances in quantum field theory and the quest for a unified theory of everything. Schrödinger's work, alongside that of other quantum pioneers, contributed to the understanding that the fundamental forces of nature, gravity, electromagnetism, and the nuclear forces may be unified at a quantum level. The search for a quantum theory of gravity, which would integrate quantum mechanics with Einstein's theory of general relativity, remains one of the most significant challenges in physics today. Schrödinger's legacy lives on in this ongoing quest to understand the universe at its most fundamental level. Schrödinger's work continues to inspire and guide researchers, as quantum mechanics remains one of the most active and dynamic areas of scientific inquiry. New experiments and technologies are pushing the boundaries of what we know about the quantum world, from the discovery of new quantum states of matter to the development of quantum technologies that have practical applications in computing and communication. Schrödinger's contributions to the field are as relevant today as they were when he first formulated his wave equation, and his work continues to provide the intellectual foundation for these new discoveries. In conclusion, Schrödinger's legacy is one of profound significance in the world of science and beyond. His contributions to quantum mechanics transformed our understanding of the atomic and subatomic worlds, while his philosophical reflections on the implications of quantum theory raised fundamental questions about the nature of reality, consciousness, and observation. Schrödinger's influence continues to resonate in the world of modern physics, where his ideas form the basis for much of the cutting-edge research in quantum computing, quantum field theory, and the search for a unified theory of everything. As we look to the future, Schrödinger's legacy will continue to guide the exploration of the quantum realm, inspiring new discoveries and reshaping our understanding of the universe.